welcome to the lecture 2. So in this lecture we basically describe the axioms of probability, axioms of probability, axioms of probability. So the probability is defined based on especially three axioms, and we will define it here. Let us consider, that is, let E be a random experiment and it is having the sample space as the sample space is S, and the class of all event, that is the all event class, we use the notation F, that is we are having a random experiment. Let E be the random experiment and S be the sample space and F be the class of all event. A probability law for experiment for E, for the experiment E, is a rule. It is a rule that assigns to each event, for example event A, which is an element of this event class F, with a number which is nothing but represented by probability of A. That is, this number is known as the probability of A, and it should satisfy the following axioms. That is, the probability law for E, that is the experiment E, is a rule that assigns to each event A, which is nothing but an element of F, with a number probability of A, satisfying the following axioms. That is, the first axiom, axiom 1, is defined as the probability of A, that is the any event A, is always less than or equal to 1, and it can be 0 or greater than 0. So it is a number between 0 and 1, including 0 and 1. That means that is 0, a closed interval, 0 and 1. So it is actually giving a measure, it is giving a measure between 0 and 1. Okay, the closed interval 0 and 1. The second axiom. So the second axiom, axiom 2, the probability of the sample space. So what is sample space? Sample space actually include sample space S contains all events. Sample space contains all events. So the probability of the sample space is equal to 1. That is the sum of all these measures. The sum of all these measures for each event, that is the measure for each event, if we sum all these measures, we will get the value which is equal to 1. So this is the axiom 2. And the next axiom, that is axiom 3. Let us assume that if there is an event A and event B, if A intersection B is a null set, then the probability of A union B is equal to probability of A plus probability of B. So for this, let us consider an example which is tossing a coin. The sample space, you know that it is head and tail. Next, suppose we are considering the event A equal to the set head and B equal to set B. Now you know that both these events, these are mutually exclusive. Okay, and that is if we get head, then there won't be any tail. So the possible intersection for this is 0. Now it is very clear that A intersection B is a null set. So in such a situation, the probability of A union B, this is nothing but the probability of having either head, or we can say the probability of having either head or tail. So in this case, it is nothing but we have 1 by 2 plus 1 by 2. So we may get either head or we may get either tail. It is nothing but 1, and it is also satisfying the axiom 2, as we know that the probability of sample space, because we are having only 2 outcomes, then you know that the sample space is nothing but the head and tail. So in this case, it is clear that it is 1. So it is also satisfying the axiom 2. Now if we are considering the set A, then the probability of A, it is very clear that it is equal to 1, sorry, it is equal to 1 over 2, which is less than 1, right? So it is satisfying the axiom 1. Now the next axiom we define is having actually mainly 3 axiom. Okay, so this axiom we can represent as 3 dash anyway. It is one of the very important axiom. If A1, A2, etc. is a sequence of events such that AI intersection AJ equal to null set for all I not equal to j, then the union of, that is A1, the probability of A1 union, A2 union, etc. so and so is nothing but k equal to 1 to infinity probability of AK, that is nothing but probability of A1 plus probability of A2 plus and so and so. So this definition is okay, but we will go something deeper into this. There are some issues and we will redefine this definition later. Okay, so we will redefine this definition later. Now let us consider some examples, and we can understand some of the mathematical patches, we can say some of the mathematical patches that may arise in defining this axiom 3 dash. Okay, now let us consider the example, that is tossing a coin. Let us consider tossing a coin which is having a sample space head and tail. Now the probability of head is is nothing but the number of favorable outcomes for head, that is only one outcome favorable to head, divided by the total number of outcome, that is 2, and so it is 1 over 2. Similarly, we will get 1 over 2 for the tail, and there is nothing here, there is no issue, it is absolutely right to define like this, there is no issue in this example. Now let us consider another example. the tossing a dice. Okay, tossing a die. So we have the sample space. There are 6 faces for the dice. We have the sample space 1, 2, 3, 4, 5 and 6. Now the probability of 1 is nothing but the number of favorable outcomes for 1, that is 1, over the total number of outcomes, that is 6. Similarly, the probability of 2 is also 1 over 6, and so on, right? And so on. So there is no issue with this. And if you notice these two sets, you can see that these sets are finite set. These sets are finite set. That is, the number of elements is finite. The number of elements is finite. So there is no issue with the definition that we have used before in explaining this. That is, what was the definition that I will we will revise it later anyway. So now let us consider another example. Example 3, that is breaking a stick having a length, for example, length of 1 meter, for example. Okay. Now, or 1 unit, you can say 1 unit, okay, of unit length. So let us consider a stick now. Let's consider a stick. This is a stick, okay, and it is a half unit length, okay, a stick with unit length. Now suppose if we break, if you start to break this stick, you can break it here or any point. Okay, now let us consider the point X. Okay, then what is the probability? What is the probability of X? So we have the sample space between 0 and 1, including 0 and 1 both, that is the closed interval 0 and 1, and X is nothing but a point. So we can say that this is a real line, for example. Instead of stick, you can consider it as a real line also. So if you are considering a real line, the number of points is infinity. The number of points is infinity. Suppose if you select any point, there will be another point which is very close to it. So if you are counting the number of points, it is not possible. It is uncountable, right? It is uncountable. So this is one of the big issue in such a case. For example, if you are defining the probability of X, you have total number of points as infinity, and your X is only just 1 point out of this infinite number of points. You can say that the probability of X is equal to 0. So there is no issue with this. But you know that if you consider the entire sample space, S, we know that the probability of the entire sample space is equal to 1. But the individual probabilities that you are getting here, it is 0. You know that this is 0, and if you sum it over all possible X, and you will finally having a result which is equal to 0. So this is a great mathematical patch. We can say it is a patch that may arise because of our poor definition that the probability of any event that we have defined like this. You know that we have already defined the probability of any event A as the number of favorable cases for A divided by the total number of cases, right? So as the number, this is nothing but, let's say this is m over n, and as n tend to infinity, right, as n tend to infinity. So but in our case, you can see that in our case we have of unit length, a stick of unit length, and you are trying to break it. Now in this case we can see that the number of points here, we can say the number of points or cases is equal to infinity, because the set is not countable or it is uncountable. So this is a big issue. So the definition that we have previously given, or this definition, is actually suffering from serious drawbacks, right? It is suffering from some serious issues. If the outcomes are uncountable, right? If the outcomes are uncountable, this may suffer serious issue, okay, if the outcomes are. So this definition is having some problem, and sometimes you may not, for example, we can say that this definition suffers from the fact that it is not easy to get the limit always, and sometimes the limit does not provide a unique value. So this is one of the important issue, one of the serious issue associated with it. Now in order to tackle this issue, we have something like, in order to tackle this issue, we need to specify the events in a different way. So I think you recall that we have already explained something during the definition. That means during this while defining the axioms of probability. A probability, actually let us consider here, you can see here we are considering the experiment, random experiment E, and the sample space S, and the event class F. So we need to define this guy, okay, we need to define this event class, okay. So we are going to define this event class. What should be this event class? Okay, if you are summing up all the events, actually you should get 1, but this event class would not be, actually, if it is uncountable, you have seen that in this case we are getting 0, and which is not satisfying the basic axiom, the second axiom of probability. So we need to define the probability, or view the probability in a different way. So we will view the probability as a measure between, or measure in the closed interval 0 to 1. So we will use some notion of the measure theory, and in measure theory you can say that you are assigning a real positive number to each set, actually, but it can be from 0 to infinity. But here in probability theory it is also a measure, but we are allowing the measure only from 0 to infinity. Or we can say that if the measure equal to 0, it implies actually the event is impossible, that is, it is clearly indicating the impossible event, okay. Now if the measure equal to 1, it is known as certain event, right? It is known as certain event. Now let us consider our example. let us consider our example of the stick that is having a unit length. Now let us consider this set. Let's say we are considering a set something like this, A1, and another set we are considering A2, and another set we are considering, let's say, A3, and so on. So we can say that for example, this is x1, let's say this is x2, and this is x3. So for each set we can assign a natural number, right? We can assign a natural number to each set, so that the number of set is countable, okay, countable. And also for each set we can assign a measure, and the measure is between 0 and 1 to each set. So in this case, suppose if the number of sets are countable, and if we can assign a measure to each set, in such a case you can see that, for example, that is for the set 0 less than or equal to x, between 0 and x1, we can, and it is denoted by the set A1, we can assign a measure which is known as P of A1, and it is a real number between 0 and 1, or in the closed interval 0 and 1. Similarly, for another one, for example, we have between x2 and x1, okay, x2 and x1, between x1 and till x2, we can assign, it is known as set A2. We can assign a measure which is known as P of A2, and it can be any real number, right, as before, real number between 0 and 1. In this case, you can see that since the number of sets are countable, okay, the P of A1 plus P of A2 and so on is nothing but summation over all I. P of AI is equal to 1. So this is one of the basic idea. So now we will in mathematics, you know that we have to describe it in a very concrete and a solid way. So we will use the idea of sigma algebra. So we will use the idea of sigma algebra. Now you can see that we have divided our unit interval into many regions like A1, A2, and we associated a measure for each one as probability of A1, probability of A2, and so on. So why we are using the sigma algebra? Now first of all, I will first define what is algebra. Okay, now actually the algebra is a word actually derived from the Arabic word algebra, right? Algebra. That is the meaning of this algebra. Actually, it is nothing but reunion of broken parts. Okay, and the name actually came from the title of the book title of the book Ilm Algebra Ilm Algebra wal Mukabala Ilm al-Jabal wal-Mukabara by the Persian mathematician and astronomer, and his name is by his name is Al-Khwarizmi. You know that algebra is a very powerful tool. We have a lot of different algebra, linear algebra, and so on. Now here we will make use of the some of the aspects of sigma algebra to define the probability theory. So what do you mean by sigma algebra? Sigma algebra. So you can see that in some textbook, where instead of algebra they will also use the terminology as a field. So the sigma algebra, what do you mean by sigma algebra? The sigma algebra or sigma algebra, it is sigma algebra on a set S is a collection, and the name of this collection we always use the notation sigma, of subset. It is a collection of subset of S that satisfies some conditions. That is, it satisfies some condition. So it is a subset of S, it satisfies some conditions. It satisfies the conditions. What are the conditions? It contains, the subset contains, that is, it means that sigma contains. We can say that sigma contains, okay. That is, the set sigma contains the set S itself, and also it is, the main points are, it is closed under complement. It is closed under complement. And the another point, very important point, is it is closed under countable intersection. Okay, it is closed under complement and closed under countable intersection. So what do you mean by this countability? The countability of a set. What do you mean by countability? You know that countability means for each element in a set we can assign a natural number. For example, natural number, that is 1, 2, 3, etc. So the cardinality of that set, suppose the cardinality of suppose we have a set A, and if each element in this set A we can assign a real number, sorry, not a real number, the natural number. If we can assign a natural number for each element, then the cardinality of that set will be equal to the cardinality of this set. Okay, both will be same. So the cardinality of A will be equal to the cardinality of this particular set of natural numbers. That means for each element we can associate a natural element. That is known as the countability of that set. So there is a countable intersection. I have actually it's not a mistake anyway. The sigma algebra, actually it is an algebra. It is a set which contain S itself, and also it is closed under the complement, and it is closed under countable union and countable intersection. Countable intersection, and this is obvious because you know there is some relationship between the union and intersection. So since it is satisfying the condition for the union, it will satisfy the condition for the intersection also. Now you have noticed that it is closed under countable union and countable intersection, and you recall that we have already explained a set F. We have already defined a set F before, and we will call this as even space, and it satisfies sigma algebra. It also satisfies sigma algebra. That means this set contains the evens, its complement, all evens, and the complement of all evens. Okay, the complement of all events. Okay, and so that's it. So, and it is also, this set is also countable. Okay, the set is also countable. That means for each element we can assign a real number, assign a natural number. So this is known as the even space. So it contains a set of all evens and its subset in a special way. That means it is closed under countable union and closed under complement. What do you mean by closed? Closed. What do you mean by closed? That means closed under, for example, closed under complement. What do you mean by this? So if X is if A is the element of this sigma algebra, let us assume that we have the set F. If A is the element of F, you can see that previously we have considered this F. So anyway, the sigma algebra, usually we denote the notation sigma, so we will use here sigma anyway. Okay, if A is the element of sigma algebra, then the complement of A will be also the element of sigma algebra. That means it is closed. It contains closed under the complement means both that element and its complement will be there in the set. So it is the closure. Okay, that is the meaning of the closed under complement, and it is closed under countable union. It is closed under countable union. Okay, since it contains the complement. So for example, okay, closed under countable union. So the another point, actually, you know that it is closed under countable union. It is closed under countable union. Now let us consider the example. We have a stick of unit length. So in this case, let us consider a set which is the open interval. So you have another part as the closed interval. So this is the set A. This is the set A. Then all other part, it also contains the A complement. It also contains A complement. So this is the regarding the first part of this definition. Okay. So if there is some measure associated with A, then there will be some measure associated with A complement. So you know that the probability of sample space, you know that the set S, that is the total sample space, you know this is the sample space. Total sample space is nothing but A union A complement. So the probability of S, that is nothing but probability of A plus probability of A complement, and this is equal to 1. So it clearly indicates that if there is some measure associated with A, which is known as the probability of A, this is the measure associated with the A, then the measure associated with the A complement is 1 minus probability of A. So this is the measure associated with the A complement. Okay, so we can view the probability as a measure. I hope that it is clear to you. Now we will discuss with some examples how to have a sigma algebra. I have already told you that in sigma algebra, we have the set sigma, which contains, it is closed under the complement, it is also closed under countable union and countable intersection. Let us consider it is sigma algebra, it is a subset, actually it is a subset of the sample space S. So let us consider the sample space for tossing a coin. Okay, tossing a coin. Then in this case we have the sample space which is equal to head comma tail. Okay, the sample space head comma tail. Now the sigma algebra, we can define it something like this. Sigma algebra for the set head, if there is head, okay, if there is head, if there is head, will be having its complement also. The complement will be tail, and also it includes the sample space, and the sample space, you know that it is head and tail, and the complement of the sample space is nothing but no outcome, that is nothing but phi. Now we can associate the measure related to, so this is an even space, actually it is an even space defined in a meaningful way. Actually it is an even space defined in a meaningful way, right? So what is the meaning of this? Suppose if you know the probability of head, this is P of H, then the probability of tail also you know, and this is the probability of sample space, and this is the probability of the null set phi. Now what is this? For example, in a tossing an unbiased coin, we have this is 1 over 2, it's also 1 over 2, and this is the sample space, so it is 1 over 2 plus 1 over 2, which is equal to 1, and this is the complement of the sample space. Since phi equal to S complement, this is nothing but 1 minus the probability of S, which is equal to 0. So the measure associated with the head is 1 over 2, the measure associated with the tail is 1 over 2, and the measure associated with the S is 1, and the measure associated with the phi, that is the null set, is 0. Now let us consider another example. So this is the example 1. So now let us consider another example, example 2. So in this case, let us see, consider the sample space, which is A comma B comma C comma D. Now the sigma algebra, that is the sigma algebra defined for the smallest sigma algebra defined on S, which contain the set A and set B. Set A and B are just the elements of this. So set A and B are defined as sigma, which is equal to, we should have the sample space, that is A, B, C, D, and the complement of the sample space, which is nothing but the null set. So the probability associated with it is equal to 1, okay, and the probability associated with the null space is equal to 0. Now we have the set A. Now we need the complement of this set. What is the complement of this set? It is nothing but B, C and D. Now if you are defining the sigma algebra for A and B, the events A and B, then we need to include B and the complement of B, that is nothing but the complement of B, which is A, C and D, okay, A, C and D. So this is how to define the sigma algebra, okay. So we can say that the complement of the set A is nothing but set B, C and D, right, and the complement of set B is nothing but A, C, D, and similarly the complement of S is nothing but phi, okay, set phi. Now suppose there is a measure associated with A, this is probability of A, then the measure associated with B, C, D is 1 minus probability of A. If the measure associated with the B is probability of B, then the measure associated with B complement is nothing but 1 minus probability of B. So we are defining the things in a special way by using sigma algebra. Now let us consider the case, our previous example, okay. Let us consider our previous example. Let us consider our previous example, okay. Let us consider the previous example, that is breaking a stick. You know that there is a stick which is having a length 0 and 1. Let us consider this as the set A. Let us consider as having, this is a set A, and the A complement is here, and there is some measure associated with this, which is P of A, and the measure associated with A complement is 1 minus probability of A. Now in this case, let's assume that this is set A1 and this is set A2. You can see that this is a countable union, right? That is I equal to 1 to 2 P of AI, that is equal to P of A1 plus P of A2, and it is satisfying the axiom, right? So similarly, like that, we can split the set into, we can split the interval, into many, right, but countable, right, maybe countably finite or countably infinite, but it should be countable. So if we are representing like that, then we can say that the union of all I, that is nothing but the union of probability of A1 plus probability of A2, this is equal to 1, because each AI is having a measure between 0 and 1, and the whole set is also countable, okay, everything is countable. Now let us assume the point in the interval 0 to 1, for example, this is x, and let us consider this is x1 and this is x2, and there is some measure associated with this is the set A, for example. So there is a measure associated with this, we can say that P of A, which is nothing but the probability that x is between x1 and x2, okay. x is between x1 and x2. So there is a measure associated with this. Okay. Now as x1 tends to x2, p of x will be equal to 0, right? The measure associated with it is equal to 0, but it is not in conflict with the notion of infinite additivity. It is not in conflict with the notion of infinite additivity, because it is because the total number of elements is not countable, right? It is not countable. So we can simply take a value in the, so what is the conclusion? So we can't simply take a value in the interval 0 and 1 and add them and claim that its total probability is 1. We cannot do it. It is because of the uncountability of the interval 0 to 1, right? So because of this we cannot take like this. So what we have to do now, we have to take an interval and we have to assign the measure to that interval, and we can claim that the countable union of all these intervals will be having a total measure which is equal to 1. So that can be done. Now with this notion we can define something which is known as probability, probability space. Okay, probability space. Okay, probability space. So it is usually represented by, probability space is usually represented by the notation S, F and P. Okay, and this S, you already know this. S is the sample space. And what do you mean by F? F we have just defined now. It is nothing but the sigma algebra defined on the sample space S. And this, what is this? This P is the probability measure, right? We are assigning a measure, probability measure. And what is this probability measure? A probability measure P is a function from sigma algebra to a real number between 0 and 1. And you know that if the real number is 0, then it is impossible event. Okay, and this 1 implies certain event. So this is the basic idea of the probability space. So it is the sigma algebra. This F is the sigma algebra. It is nothing but set of all outcomes. It is the set of all outcomes. So what do you mean by the sigma algebra? It is the set of all. It is not the set of all outcomes. It is an algebra which is defined by using set of all outcome, and we have already defined it. Okay, so it is an algebra which is defined on set of all outcomes. I think it is clear to you, right? Now we can consider Now our problem, that is and you know that the sigma algebra always contains a set and its complement also, and so because of this property the total measure will be equal to 1. If one element is having a measure 0, then its complement will be having the remaining measure, right? So if for every element, if we are defining a measure, and if the even space contains its complement also, then it is very clear that the total measure will be equal to 1. So this is how we solved the patch which has arisen in our basic definition that we have used before. Okay, now let us consider another example. Let us consider another example of a real line. Okay, real line, let's say R. So we have a real line which is extending from minus infinity to plus infinity. Now we are defining a function, let's say this is the function, this is a function we are defining. Let's say, assume that the function is g of x. We are defining a function g of x, but the g of x is having a property that the area under g of x, that means integral minus infinity to infinity area under g of x dx is equal to 1. So the area under g of x is equal to 1. Now let us consider 2 points, let's say x1 and x2. Now let's consider some arbitrary point, let's say some arbitrary point x. Okay, now how we can define a measure by using this function g of x. So how to define a measure? Now the measure, we usually use the notation p of something for denoting the measure, because we are talking about the probability theory, right? We are talking about the probability. So that's why we will always use p of the function as p. Now the probability that the variable x is less than or equal to x1, we can say that it is nothing but integral, that is we have to start from the minus infinity till the value at x, okay, till x1. Okay, now we have to integrate all the value till x1, the function g of x. So this is the measure, actually this is the measure for x less than or equal to x1, and we will call this measure as the probability that x less than or equal to x1. Similarly, we can define x less than or equal to x2 as integral minus infinity to x2 g of x dx, and this is a measure, this is also the measure for x less than or equal to x2. So in this case, now suppose we want to measure what is the measure corresponding to the points, let's say it is here, the points is here, that is between x1 and x2. So we can say that between x1 and less than or equal to x2, the probability we can define as x1 to x2 g of x dx. Now what is the probability for the whole space? What is the probability for the whole space, right, in the real line, or we can say that the whole real line, that is probability that x less than between minus infinity to infinity, which is nothing but integral minus infinity to infinity g of x dx, as we defined before, we know that it is equal to 1. So by using a continuous function, actually by using a continuous function g of x can be used to define the measure. So the algebra corresponding to this, you can say, suppose you are considering this closed, you are considering this minus infinity to infinity, you can assign some set here, right? Let us set a1, and let's say this is the a complement. In this above case, we have the function, this is g of x, okay, and we have the set, this is a complement and this is a complement. Then even though we have infinite number of points, the probability of this a complement, if we are defining a proper sigma algebra, the probability of a complement is 1 minus the probability of a1 complement, that is a1 complement is 1 minus probability of a1. So it is possible only if we can define the measure for the specified set. So if we can define the measure for the specified set, we will automatically get the measure for the complement also. So this is the case. Now we will see what will happen in this example when x1 tends to x2. That means these 2 points move to some point, and we can say that x1 equal to x2. So integral x1 to x2 g of x dx is nothing but the probability of a single point, let's say x1, if x1 is tending to x2, and let's assume that x1 equal to x2. In this case, we will get a measure 0, and there is no issue with this. So I hope that the idea is very clear to you. Now we have defined the probability space as fp with s as the sample space. Then this is the sigma algebra, and this is the probability measure, right? This is what we have explained. Now let us consider the example of tossing a coin. In tossing a coin, we are only having some finite number of events. That is, we are having only 2 events. It is finite number. And rolling a die, right? Another example, rolling a die. You know that the sample space contain 1, 2, 3, 4, 5, 6. Okay, only 6, not more than 6. Okay. So here in these two sets, it is evident that it is having only finite number of elements. So because of this, we don't need the complications, right? Like sigma algebra, all these things are not required for explaining this. So in this case, a simple probability space with the sample space and a measure p probability, that will be sufficient in this case. But in general way, in a generic case, actually we need the concept of probability space. So we can define the axiom 3 now, axiom 3 dash, more in a concrete way. That is, for any countably, see the word countably, for any countably, this is very, very important, infinite, because we are defining the even space as the countable number of spaces, countable number of sets by using the sigma algebra. So without sigma algebra, we could not be able to explain like this. So for any countable infinite number of mutually exclusive events, let's say a1, a2, a3, maybe it will be infinite, but it may be countably finite or infinite, whatever, each belonging to sigma algebra, right? Sigma algebra. we have probability of A1 union A2 union and so on will be equal to probability of A1 plus probability of A2. This is the definition. Okay, here you can see that all this A1 A2 everything is belonging to the sigma algebra. It is belonging to sigma algebra. Okay, this is equal to summation I equal to 1 to infinity, maybe infinity, probability of AI. Okay, this is the one of good definition for axiom 3. Now I will give you a problem, that is example. Try to find out the answer for this. Tossing a coin n times as n tends to infinity until the head, that is head, appears. Okay. Now you see here, what is the event 1? Suppose you toss the coin, in the first time itself, suppose you are getting the head, you stop with that, right? We will call this as the event 1. And let's say event 2, maybe in the first trial you will be getting head, then in the second trial you will be getting tail. Okay, and this is known as omega 2. This maybe the third possibility, the first 2 trials you will be getting the tail and then you will be getting the head. We will call this as omega 3. And the fourth event we can consider, it is the tail, head, and this is omega 4. So the sample space for this omega 1, omega 2, omega 3, and you can see that there are having infinite number of elements. So if we are defining the probability by using the very basic or very basic definition that we have discussed in our first lecture, like the total number of favorable outcomes by total number of outcomes, in that way if we are defining, you can say that there are infinite number of elements in this, so that the probability of each event will become 0, and the summation you will get 0, which is something not make the sense. So in such a case, actually we need the idea of sigma algebra to explain. So try to find the sigma algebra. Okay, find the sigma algebra for this. I hope that this is clear. Thank you.